Cool. Do I have a dog? No, we don't have any pets. We used to have a hamster, but can't mention that too much. You mad that I don't have pets? We have a lot of allergies in the family. The hamster was named Pork Chop because he was a hamster. I didn't make that up. Yeah. Cool name. Yeah, that was my son's name. I mean, his name for the hamster. Phil. Wait, what is that from? Yes. Just Phil. Let's see. Let me start typing stuff about upcoming things. So I'm making additional changes to that. He only had a master's. Right, because he wasn't doctor. Well, Dr. Phil, what is he a doctor of? In the old days, people used to joke that MD stood for money doctor versus PhD, which was phony doctor. Yeah. Yeah, I know. It's so rude. So here, let's do. So I made some changes for the schedule. So I'm pushing things farther back, and that doesn't mean that we're going to cram everything together at the end of the semester. If I space things out more, yeah, we'll just have a little bit less of everything. So more time is nice. Yeah, I don't. Yeah, our job is to get by, learn what we can without causing undue difficulties. So Friday, two things. We've got, keep reading ahead. We're getting a little bit out ahead, but it's okay. Of course, I haven't posted the warm-up for this one, so I better post this warm-up. And then the other thing is 3 p.m. There's the physics celebration. Oh, it helps actually for me to share this out with you. Hey, Harry. What's up?
For the physics celebration, are we supposed to dress nicely from the waist up?
You can just dress from the waist up, please. And the waist down,
okay.
Too. Yeah, no, you don't have to be dressed nicely. You do have to be dressed.
Okay.
That's all we got. Yeah. No, it's usually just like, getting people together in a conference room and having cake. So we're going to get together in your whatever, everyone's respective spaces by Zoom, and you can have your own snacks. And it's just like, hey, let's hang out, socialize. I hadn't figured out the quiz yet, and so let's push it back even more. It's, like I said, going to be low key. I haven't fully figured it out, and so likewise, if we're pushing that back, let's push the homework back. Cool. All right, so going with this stuff here, let's talk about complex numbers again. And if you can, actually, oh, sorry. What I'd like to do, actually, what I'll do is just for talking about them, I'm going to go back to the sharing the PDF, and I'll point at it. But then we'll do some problems together on the whiteboard. And oh, I closed it. Bear with me one moment again. And okay, let's see. Is it appearing okay? If I move it over here, it's a little bit shaky when I move it, but otherwise looking okay. All right, so here we go. We were talking about our complex numbers. Why are we going to use complex numbers? One of the reasons is we can use them to include this idea of phase. So complex numbers we see right here, naturally, if we just do e to the I times an angle, it naturally turns into a cosine and sine. This looks a lot like the waves we're going to be using. And we talked about how there are two ways to represent them. One is kind of the Cartesian coordinates, where we break it up into the real part and the imaginary part, right? The real part and the imaginary part. Or the other way is a polar notation way, where we have a magnitude times the phase right here. And we can graph these on our coordinate system like this, where we've got the real axis and the imaginary axis. So real plus imaginary gives us complex, the complex plane. But the other way we can represent this same point, this is z, right? It has a real component and an imaginary component. The other way we can talk about that is a modulus, and then a phase is the angle around we make like this. And just, without doing a full-on proof, just graphically, we can see that the modulus is going to be equal to by the Pythagorean theorems, the square root of the sum of the squares of the real and the imaginary components. And that's what this thing right here is saying. And we can kind of see that if we write this out, z, and we expand this e to the I theta out into cosine theta plus I sine theta. If we were to multiply that out, and we'll see what that means in a moment, we can get a cosine squared and sine squared somehow. How is that going to happen? We'll see in just a second. But it's kind of believable. Cosine squared plus sine squared looks a lot like a real squared and plus imaginary squared. Our complex number is a mathematical tool. Yes, so that's a really deep philosophical question. Are they? And let me actually see how you phrase that again. I'm going to switch over to the chat. Does it have a physical meaning by itself? So in this situation, right, we are doing this. You could do waves without the complex number. So in this situation, they're going to be purely a mathematical tool. The math would be pretty atrocious without it. So it's a really useful mathematical tool. It turns out that as we get farther along, there are going to be points where, yeah, it would almost be impossible to see some of the connections without the complex numbers. And then when you get to quantum mechanics, it's really essentially impossible to do quantum mechanics without complex numbers. And so then again, in quantum mechanics, there's a lot of people struggling with what the actual meaning of quantum mechanics is. Let me see, I'm going to see if I can quickly switch back and answer your question in a different way, though. I'm sorry. Hey. I'm going to derail myself a little bit and digress, and but try to answer your question a little bit more, Carter, to provide a little bit more motivation. So when we think about a wave, right? If I just go like this, right? Let's imagine we were looking at this with this thing coming directly towards us, right? So an end-on view. So here's side view. Oh, I was trying to do that with my mouse instead of my pen. No wonder it was so sloppy. There's the side view. And so here's an end. Sorry. I got to position myself a little bit better here. There's a side view. Here's an end-on view. And you have to watch. Can you see me as I draw each letter, everyone, or does it just the letter itself appear? Can you see the line coming, or is it just like each letter appears when I finish the stroke? It just the whole thing appears. Okay, so that's going to change how I show this. So let's do the end-on view, and so I'm going to draw. So we're looking like we're on the right-hand side of the whiteboard, looking towards the left side. And what do we see? We see the wave kind of going up, 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 and then down, 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 like this, right? It's just oscillating up and down. And so we can, so if you look at that part right there, that it looks like actually just the projection of something that's going in a circle. And actually, I should have drawn this all sideways, but it's kind of like something going around and around in a circle, but we're just taking the projection onto one axis right there. Right? So it turns out we're going to use complex numbers to represent our waves, but we're just going to look at the real component of them, and the rest is there as a tool to help us, but it doesn't have a physical meaning. But we can imagine it really kind of like the wave. If I were to draw, a bunch of vectors to each of these things as it goes up and then goes down and goes up, right? What's happening here is the vector is going around in a circle, right? And so we can imagine in this complex space, the electric field, complex electric field is doing this, but really what we're looking at is, again, the projection just onto one axis. So the vector goes up and then it comes back down and it starts going down and a little bit less, a little bit less, then back up, etc. Kind of helpful? Are the dots the electric field? So the dots were the location of the tip of the electric field vector, say, as I went around. And then the lines were supposed to be electric field vector in complex space, though, right? And so if I were to draw a picture of this, right, in terms of a complex space, right, I could do it like this. I'm going to draw this axis like this. So instead of just going up and down, I'm going to make this axis right here. We're going to turn it on our heads on our sides. So this is going to be the real part of, and this is the imaginary part. And then like this is Z as the wave propagates along. And so instead of just having a sinusoid, what we're actually going to have is something that, here's the end of it. So it's going to be hard to see until I draw, crud, sorry, this was supposed to be like this. Well, anyways, let me draw the electric field vectors. Really what this is like is actually it's supposed to be like a corkscrew. It always has the exact same amplitude, but the projection onto the real axis is what changes. So I didn't do the greatest job, but you can think of this as being like a corkscrew. So we don't ever actually have to change how big the electric field is in complex space, but the projection onto the real axis is what varies. Ooh, fancy, right? All right, so let me quickly, I'm going to actually take a snapshot of that, and then we'll go back to complex numbers. So I can't imagine that fully satisfied everyone, but I'm hoping it provides just a little bit of motivation for like why we're doing some of what we're doing with the complex numbers and what they're going to mean. All right, give me one moment. This is just always like several times more cumbersome than doing it in person.
Oh my God, it worked.
What worked?
Blackboard virtual classroom finally works.
All right.
Oh,
Okay, so drawings of a complex wave. All right, I'm going to leave that off to the side right now. Let's go back to here. Let's stop this and put up complex numbers again. Oops, I actually have to press share again. There you go. Cool. All right. So we've got our complex numbers. We've seen how we can plot them on the complex plane and describe them in terms of real and imaginary parts, like Cartesian coordinates. Uh, we're happy for you too. We're all happy. Or we can talk about a modulus and a phase, and that's going to be like polar coordinates. So next thing we're going to do is we're going to introduce this new operation. And what's not written on this notes, oh hey, look at that, is that this operation is called taking the complex conjugate. So complex conjugate is z star right here. So we indicate the complex conjugate with z star. So two different ways well, multiple different ways to write this, right? One is we leave the real component alone and we put a minus sign in front of the imaginary component. So instead of being a plus IB up here, becomes a minus IB, or again, the real component, then minus the imaginary, the old imaginary component. Another way to write the same thing is we leave the modulus the same, and we write e to the minus I theta now is the complex conjugate of what z was, where it used to be modulus of z times e to the I theta. Complex conjugate of z is modulus of z times e to the minus I theta. So the simple way to remember both those things is anywhere there's an I in any expression, you just replace it with a minus I. So that's true of simple expressions like this and like this, but it's also true when we get to more complicated expressions as well. So everywhere there's an I, you replace it with a minus I. And so on our graph of the complex plane, if this was z right here, right, the real component remains unchanged, the component is unchanged, but the imaginary component of the complex conjugate is the negative of the original imaginary component. So one way to think of that is instead of going up by imaginary of z, now we have to go down by imaginary of z because it's negative imaginary of z is the imaginary component of z star, the complex conjugate. And you can see that reflection is also the same as rotating by an angle theta in the negative direction right here. So two ways to think of it. One is rotate in the negative direction. The other way is reflect it over that real axis right there. And so we're looking at two different ways we're looking at multiple representations of the same idea. Here we're looking at a graphical representation, and here is a symbolic representation. And in both cases, we did it in terms of a Cartesian way of describing it versus the polar coordinate way of describing it. So once we have that, we can actually talk about a handful of other things. We can actually now use the idea of complex conjugate to define the modulus. So the modulus squared is equal to z star times z. And we can think of it this way. I'm going to see if I'm going to try to write on here. Give me one moment. It's trying to go between two different things. Okay. No, stop it. One more time. Yeah. Oh, forget it. Oh, wait. No, that's a fill-in sign. One more time. And then I'm going to give up. There used to be a draw on tool, but I guess this isn't the right kind of document for PDF document for that. Forget it. All right. So let's take a look at what would it be if z is a plus ib. Yeah, I'm going to close that. Z is a plus ib and z star is a minus ib. We can, if we were to write z times z star right here, that would give us, sorry, I'm still looking to see if I could draw. I'm going to just add a sticky note right here and type in there. So what would it be? So we'd have A plus IB times an A minus IB. And so when we go to multiply those out, it's going to be, we're going to FOIL it. So first you'll get A squared, cool, that's fine. And then outer, so we get a minus IAB, and then inner we get a plus IAB, and then the last we'd have I times minus I. And remember, so we'd have a minus I squared times B, and B squared. And now remember, I squared is -1, so that last term becomes plus B squared, right? And so we've turned this in, and notice the cross terms right here, the AB terms will cancel out. So we end up with just A squared plus B squared, right? And that is, if A is the real part and B is the imaginary part, then what we've got is real squared plus imaginary squared, and it is equal to the modulus squared. And then, okay, if you just want the modulus, you take the square root of that. So hey, it works out. That's how we can start with that actually as our definition. So one of the things we can see then, yeah, tools, comment bar on the top. Comment, that's what I was looking for. Thank you. That's what yep. It wasn't editing the PDF, it was doing the comments. I'll come back to that if we need it then. All right, so an important corollary of this is that the modulus of e to the I phi is equal to 1. Right? And so we can take a look at this actually two different ways. One way is e to the I phi, the modulus of that is going to be equal to the square root of the modulus squared. So the modulus squared is the complex conjugate of it times the original quantity. So the complex conjugate of e to the I phi is just e to the minus I phi. And then when you multiply them, that means you add their exponents. So it turns into the e to the 0, and that turns into a 1. Cool. We could also show the same thing if we did it out with this thing right here, right? Because we would end, when you multiplied the complex conjugate of times itself, we get a cosine squared, we get a minus I sine theta times an I sine theta for the last in foiling it. And the cross terms, we'd have a cosine theta times I sine theta, and then we'd also have a minus I sine theta times the cosine of theta, and that would cancel out. And so we'd end up with taking the square cosine squared plus sine squared, which is just equal to 1. Yeah, e to the I theta is always modulus 1, right? And so that's useful. What we're going to see is what that multiplying by a phase factor like that. So the phase is the argument, but the phase factor, e to the I theta, doesn't change the modulus, but obviously it changes the phase, right? Because when you multiply by an exponential and you've already have an exponential there, that means you add their exponents. So that's why it's really, really useful. It turns like multiplication into addition. That's kind of one of the nice things instead of having to do trig identities. So yeah, trig identities, avoid them if you can. What else? So other handy rules. The complex conjugate of a product is equal to the product of the complex conjugates. Really straightforward. There are generalizations of this, and it turns out that you got to be a little bit careful in some of the generalizations where order matters. What else? The modulus of a product is equal to the products of the moduli. Yay. Cool. Here's a cool one, right? The real component is equal to half the sum of the quantity of the complex number and its complex conjugate. And you can see that, like, if we add, if z is equal to a plus b, here, let's try this. Whoop. There we go. Let's see if this is any better. So, right, if z is equal to a plus ib, let's see if I write just right here. Ooh. A plus ib plus a minus IB, all that, whoop, divided by 2, right, is going to be equal to 2A over 2 is equal to, because the IB parts cancel out, and that's just equal to A, which was the real part. So that's another little handy thing to keep track of right there. And you could do the same thing right here with to get the imaginary parts. Right. So we subtract them, and that means that subtracting a minus IB from IB will give us 2IB, and then the A parts here cancel away. But then we also have to divide out that extra I to get the B, the imaginary part, just by itself. What else? If the complex conjugate is equal to the number itself, then remember down here, right, that means that when we did the reflection or the rotation, we ended up back at the same place. So that's only going to be true if you're on the real axis. So that is if it's like a real number. And similarly, if you taking the complex conjugate just completely inverts it, so multiplying by -1 is going to take you through the origin in the exact opposite direction. So if you get exactly, when you take the complex conjugate reflecting over the axis, you get exactly the same thing but with a minus sign. That means to only have imaginary components, because if there's some real component, then it wouldn't pick up the minus sign. The real component wouldn't. So we're denoting the reals with this whatever special font R, and the imaginaries with a special font I. What else? So we know that I squared is equal to -1, so we can just do a bit of rearranging, and we can see that 1 over I is equal to, this is the same as negative, right? Because if I cross multiply the I over to this side and then divide out by -1, I can come back to I squared equals -1. So that's another useful thing. If we have i's in the denominator, we can do that. It's kind of, because particularly since this imaginary thing, what we're eventually going to do is just take the real component. So it's nice if we can just slice off that real component and throw it away. And you can't do that when stuff's in the denominator. You can do that if it's for stuff in the numerator. You just throw away the terms that are imaginary in the numerator. But you can't do that in the denominator. So we're often going to want to take something that has a complex denominator and make it so that the denominator is entirely real. And it's kind of like rationalizing a fraction with square roots. Exact same process. Look familiar? Even include it. So what you do is you take the complex conjugate. So basically you take the imaginary part you're trying to get rid of, and put a minus sign in front of it. And you're going to multiply that, but I mean, you have to multiply by the same thing in the numerator and denominator so that you don't change it. You know, you're multiplying just by 1 overall. You do that, and when you multiply by the complex conjugate, you just get the square of the real part plus the square of the imaginary part. So it's entirely real. And then you get still have a complex numerator, but that's fine. It's a lot easier to live with that than with a complex denominator. Excuse me. So I had to get a drink there. How are we feeling about that? Sort of comfortable, a little bit confused.
I'm a little bit confused, but
okay. One of the things we're going to do is we're going to practice stuff with complex numbers coming up in just a moment. Because right there, that was just a whole bunch of like, oh, here's the property, here's a whole bunch of properties. Do you understand them all? Well, you got to practice with them to understand a little bit better. But I wanted to give a little bit of a pause, see if people had questions. So before proceeding, I'm going to add just one little bit right here. So this multiplying thing. So if we think about our complex numbers in polar terms, right, in as polar coordinates, right, where it's a modulus times a phase factor. So z e to the I theta, and then for w, it's modulus of w times e to the I phi. Why phi? I just needed a different angle name. So if we multiply them, right, we can multiply their moduli together, and then we're going to multiply these exponents together. And when you multiply the exponents, you add, when you multiply the exponentials, you add the exponents, right? And so what that's doing is we're still multiplying the moduli. So if z and w are both bigger than 1, zw is going to be longer still, right? But what's going to happen is the new phase will be the sum of the two phases. Right? So if z was at theta and w was at phi, then zw, there's a mistake right there, by the way. Zw is going to be at theta plus phi right there. This thing right here, this should just be a times, right? That's that length right there. I'll post a corrected version of this if I can. All right, so these things are all on Blackboard. You've got it recorded now in this lecture, but the document itself is on Blackboard for you to access. So what I'd like to do before we just jump in and start using this is let's start out a little bit more gradually. So for this, I'm going to pause sharing this stuff right here. I'm going to open up a whiteboard, but if you could go to, resources. In resources, the same place where this is stored, there's it's called complex. Complex review is actually, should be titled complex practice problems would be a better name for it. So I'm going to open that up, but I'd like you to open that up for yourselves too. And we're going to work on that some together on the whiteboard once I shift all these windows around so I can see them. So here, actually, why don't you, if I could ask you to give me a happy face when you've opened up the complex review document. Okay, I've got 4 people who found it so far. Oh, that's a commented happy. Oh, thank you. He's multiply happy. And there's, so Aaron, all right. That was Nate. So Harry and Carter are still looking to open it up.
I got it. I just forgot to put the smiley face.
Okay, so everyone's got it. Cool. All right, so let me go back and share the whiteboard. All right, so let's talk about this. You know, in class, normally we would break up and work on this in groups. I think that would just be really, really cumbersome. It would be useful, but cumbersome. So let's through them. And I'm going to maybe ask people to tell me what they're thinking. And here, I'm going to look at the participant list. And it has it alphabetized. And what we're going to do is we're going to go through it alphabetically. But if you're not comfortable, you can say, you can just ask the next person what they think too. So let's just do 1A. This is going to go to Amy. What do you think about 1A here? So this is, we're trying to find z plus w, and if z is, here, z is a plus ib, oops, and w is equal to c plus id. I'm going to try to make my eyes a little bit curvy on the bottom so they just look like ones. So Amy, what do you think about this? What should I do here?
I have not read the question.
Okay, so 1A is just finding Z plus W. Do you want to? Let's see. How about Camille? What do you think about this one here? Whoops. Oh, is Amy writing that? Who's writing that? Camille. Hey. All right, cool. You can also dictate it if you're finding it hard to write, but you're doing pretty good. You're doing well. All right, so we got Z right there, and we got to add in W. There you go. That's perfect. Awesome. And we'll see how this works. If not, like, I don't know, we'll C plus ID. Yay. Cool. All right. And is there anything more we need to do? Well, if you wanted to, I could gather the real parts together. This isn't necessary, but if you wanted to, I plus I times B plus D, right? And now we still have it in terms of a real part plus I times the imaginary part. All right. Here, let's go to Carter.
That's it.
That's it.
Wow.
So these things are complicated sounding and scary, right? Because it's new. It's this whole other degree of freedom. But we can do addition. All right, let's add on. So let's talk to Carter next. How are we going to handle this? And you can just dictate it to me, and I can write it if you don't want to write it out. But let's do this right here. Z plus W star, which we're going to read that as complex conjugate of W. We can also say W star.
So this one I think will just be A plus IB then plus C minus ID.
All right, so W, when we take the complex conjugate, you've got that right there. We turn the I into a negative I. And so, again, if you want to, not necessary, we can gather this together, A plus C plus I times B minus D. Right? And so this complicated sounding operation, complex conjugate, just turns into multiplying the real bit, I'm sorry, the imaginary part by -1, so that when you're adding, you add together the real parts and subtract the imaginary parts. Okay, so here, this is going back to this graphical bit right here. And this is one I want everyone to ponder this one, because this one's a little bit hard. So complex conjugation, right? So here's the imaginary axis. Whoops. There's my Z right there. And then if this right here was Z star, complex conjugate as Z, right? And that's a reflection about the real axis. What corresponds to reflection about the imaginary axis? What operation? And so can we express it in terms of things we already know, like taking the real, taking the imaginary, taking the complex conjugate, taking the modulus? So reflecting about the imaginary axis, we're talking about being right here. So it says, Derek, do you have any thoughts on this? How could I make this thing right here? What was that? You're not sure? I'm just hearing about you. Okay, no worries. How about this? Anyone have a suggestion here? Let's just put that out to the whole class.
Negative of the complex conjugate?
Okay, that was Jake. Yeah, Nate had his hand up too, right? So notice one thing right here, right? So we could write in all kinds of ways, but a very compact way to do this is that this is just negative of the complex conjugate, because negative means going through to the opposite side of the origin, right? So if this is Z star, this is negative Z star. Just like, no, don't be sorry. That was perfect. Thanks. Yeah, we can do hands, but yeah, it was good. All right. Lightning round. Let's do. All right, so we did. All right. Really. All right. So what is this? Let's go. So we did. Derek, Jake. How about Harry? What is e to the I pi? What do you have to think about that?
So e to the I pi will be -1, because if you
Oh.
imagine a unit circle, it'll go all the way over.
Okay, so Harry's imagining this right here. And I'm going around.
And I only happen to know that off the top of my head because differential equations talked about it literally this morning at 9 o'clock.
Sweet. Yeah. So this is one way to look at it, right? This is an angle of pi, and it's on the unit circle. So that corresponds to -1, right? And like all angles, we're measuring it from the x-axis, from the real axis right here. Right? So that's pi. There's another way we could do this, right? So one way is the graphical way. Another way, does anyone have off the top of your head another way to measure this or to find out this? Oh, so it's equal to -1.
Could you explain the graph a little bit more? I'm confused how.
Okay. So on
Is
this
it just a
graph,
reflection over the.
it's not a reflection. What we're doing is we're working on we know that e to the I pi, I'm sorry, e to the I theta is always going to be on the unit circle because we know the modulus of e to the I theta is equal to 1. And so the question is, how far around the unit circle do you go? So we start on the real axis right here, and we go around by an angle of pi, right? Pi is 180 degrees. And so that leaves us right here on the real axis, but on the negative side, right? We can think of this like being like a number line, right? Positive real going down to 0 over to negative real, but then we can also go off in an imaginary direction, positive imaginary direction, negative imaginary direction, or some combination of the two, or complex numbers. So again, e to the I, anything is going to lie on this unit circle. Yeah, okay. Carter's jumping ahead too. Number D, letter D, part D. Yeah. Cool. So I'm going to jump ahead. We're going to do this over here. D, right? E to the I pi over 2 is equal to just I, right? Because what we're doing is we're going from here up to there. Before we do that, and actually we'll come back to that one, but let me go back to A right here, e to the I pi. Here's another way to do this that's not graphical. We know e to the I pi is going to be equal to this cosine of whatever that argument is, in this case is pi, plus I times the sine of the argument of the exponential, right? And so this is going to be cosine of pi is 1 plus I times sine of pi is 0, right? Oops, sorry, cosine of pi is -1. That's pretty important. So -1 plus I times 0 is just -1, right? So that worked too. And let's do the same thing over here, actually, for letter D. So e to the I should have left way more room, over 2 is equal to cosine of pi over 2 plus I sine of pi over 2, right? Cosine of pi over 2 is 0 plus I times sine of pi over 2 is 1. So I times 1 We're cool. We got the same answer both ways. Yeah, it's like a trig circle with x's and y's, except the y-axis is the imaginary axis. Yep. So, and that's so it's kind of like just a tweak, a modification of stuff that we already know. And in fact, right, in some ways, what in terms of the history of things and the order in which we learn it, right, this is in some ways seems like an extension of trig. But once we actually get there, we could actually start with complex numbers and just say, hey, trig is just a special case of all this complex number work. So let's do some of the intermediate ones. Let's do letter B, under 2. This was e to the minus I pi. So let's see. How about Nick, right? Or Nate. Let's do Nate was the next going down the list. What do you say for e to the minus I pi?
So it's going to be e to the minus I pi is going to be cosine negative pi plus I sine negative pi.
Mm-hmm. Okay, perfect. Can you start to evaluate those now? Because that's a good start. Cosine of minus pi. Whew, what's cosine of minus pi?
0.
Oh, not quite, not quite.
Oh, wait.
Oh,
Oh, wait, yeah, I was thinking vertical. Be -1.
-1. Cool. And then what's sine of negative pi?
0.
0, right? And so we get -1. Hey, that was the same thing, right, as what we got for A. So let's do graphically, once again. If this is the imaginary axis, here's the real axis, right? So we're going to go around the unit circle again, but we're going to go negative pi. So that's like going around like that, starting from here, going around like that. And so, yeah, we still end up at -1. Nicely done. Nick, how about what is e to the 2 times I pi? That looks a little bit different. I don't know. Nick, do you have thoughts on this? All right, let's put up a hand. We'll do hands up. Someone got a suggestion. Derek, yes.
Oh, would it be 1?
Would it be 1? Yes. Ding, 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 ding. No buzzers, right? So how did you think of that? How did you come up with that?
Well, I did the cosine 2 pi plus I sine 2 pi.
Right. So cosine of 2 pi plus I sine of 2 pi. So that's equal to 1 plus I times 0, right? And again, what we're doing is we're going around, ending back up at 1. So we made the angle is 2 pi. That puts us back on the real axis right there. All right, give me 1 second. I'm going to move over to a new board in just a moment. Okay, cool. Get that out of the way and wipe this. All right, so let's do, what are we on now? We are on, we did 3D, let's do 3E. So e to the minus I pi over 2. All right. Looks like we've wrapped around to back to the start. So, Amy, do you have a feeling about this one right here?
Would it be negative I?
Negative I, indeed. Yes. So how did you get that?
So it's like D, which we already did, so it would be cosine of pi over 2 minus I sine of pi over 2.
Yeah. So, yeah, and so two different ways to do it. You could do cosine of minus pi over 2 plus I sine of minus pi over 2, right? Which is going to be equal to 0 plus I times a negative 1, right? And so overall that's minus I. But another way to look at it actually is we know that e to the minus I pi over 2 is equal to e to the I pi over 2, which we already did, right? Take the complex conjugate of that. And because this is purely imaginary, we're going to end up with, right, since purely, sorry, since e to the I pi over 2, purely imaginary, e to the I pi over 2, sorry, complex conjugate equals negative e to the I pi over 2. And I'll give us a third way to look at this, right, is we're just starting from the real axis and going negative pi over 2 down to there. Okay, cool. So lots of different ways to approach the same question. And it's going to be, like a lot of other situations, it's going to be useful to kind of move fluently between them. A lot of times it's, pick whichever one's most convenient, most handy for you. But it will be useful to kind of move between a geometric, graphical versus, numeric or symbolic approach. All right, so the next one was e to the I, pi over 4. Getting a little more complicated. Let's see, who's next down the list? Camille. What do you think about this one? Oop, there we go. It's hard, right? Oh, it's hard to write. So are you saying root 2 or are you still writing? That's your answer. Ah, okay. So you've got it definitely involves root 2. But that's not quite all of it. Oh, I was going to write it out and explain it. Okay. Here. You're very much on the right track. Derek had his hand up too. What do you have to say there, Derek, or no?
I mean, Camille, you can continue. I'm not gonna butt in on you.
Cool. Hugh, so Camille, do you want to do it with sines and cosines, or do you want to do it graphically? I'll let you choose. Cool. Now I'm getting an appreciation for what you folks see when I'm writing too. Nice. Yeah, that's right on. So let's just double check these things. Cool. So first term, cosine of pi over 4. So it was root 2. Oh, I think I know where you got the root 2 as your full answer. Cosine is root 2 over 2. Yep. All right, I'll let you do. Yeah. Yeah, that is correct. Yeah. So it depends how you uh, like to think of your cosine and sine of pi over 4. So if you like them as root 2 over 2s because you don't like square roots in the denominator, then we're going to have root 2 over 2 plus I times root 2 over 2, right? But root 2 over 2, that's the same as 1 over root 2. So then we've got 1 over root 2 plus I over root 2, which we can gather together the way Camille did into 1 plus I over root 2. And you can double check this, even though this is 1 plus I, this still has a modulus of 1, right? Here, let's just do a really quick check. Well, we know that it should be equal to 1 because if we multiply, obviously, so here, question mark equals, right? So this right here is going to be equal to 1 plus I over root 2. And then we can multiply that by 1 minus I is a complex conjugate. Oops, I'm sorry. So since, right, so this is equal to e to the I pi over 4 times e to the I pi over 4 complex conjugate. And of course, you could do the complex conjugate just by putting a minus sign in front of the exponent in the second term right there. And then when you multiply them together, you get e to the 0, and so that's 1. But let's do it out this way too, right?
I'm
So
confused how you converted it to the 1 plus I over root 2.
oh, and this is, I'm sorry, let's make sure that this is, so how did Camille do this part right here?
Yeah.
Yeah, so another way to write this right here is this right here is equal to, well, root 2 divides into 2 root 2 times. So this becomes a 1 over root 2. And this right here becomes a 1 over root 2. So it's I times 1 over root 2 in the second term. And then since they both have root 2's in the denominator, she just collected them into 1 plus I times 1 all over root 2 for this right here. That help, Derek?
Yes, thank you.
Cool. All right, so we're doing all this, and so let's multiply these all out. We get a 1 first, then outer would be a minus I, and then a inner would be plus I, and then last would be minus I squared, all that over regular 2, because it's root 2 times root 2, but all under the square root. I overwrote some of what I was trying to do. So notice the I and minus I cancel out, and so we get a 1 plus I squared minus I squared, which is a minus minus 1, so 1 plus 1 over 2, take the square root, and hey, that's equal to 1. We're good. All right. And let's just wrap up with G then. Cool. G was e to the minus I pi over 4. Oh, and I forgot to say, like, for all this stuff up here, right, we were just going to that point right there. Right, so we can do cosine and sine. What's next? Carter, do you have thoughts about this?
My answer was root 2 over 2 times the quantity of 1 minus I.
Okay, yeah. And that's yet another way to say the same thing. Not the same thing. Another style of expressing something similar, right? Which we could also write as 1 minus I over root 2. And looking at this, we can see that, hey, yeah, this really is the complex conjugate of the previous answer, right? In F, we had 1 plus I over root 2. Here we've got 1 minus I over root 2. And notice that this right here is the complex conjugate of that right there. So that makes sense. And of course, we could also do it with sines and cosines, taking a look right here on our real and imaginary axis. This is going to be down around to there. Same deal. And right, notice it's got a positive real component right there and a negative imaginary component right there. All right. Let me quickly save a picture of this. Then we'll get into more interpretive type stuff, making meaning out of this. Okay. All right, so here, question, whoa, wrong place. Question 4. Graphically, what does A of Z do to Z if A is real? And let's, for the time being, let's imagine it's real and greater than 1. Anyone? I'll take a hand for this one. So I'm going to put Z, let's imagine Z is right here. That's not a hand. Imagine A is bigger than 1. Someone want to stick up their hand and tell me, what does A of Z look? Jake, you want to draw on there or dictate to me, what would A of Z look like for A greater than 1? Whoops, 1 and A. What would you have to say? You can also draw it on there. All right. Yeah, I like it. He's out here. Cool. You're learning what I'm going through.
I'll let you finish that.
Yeah, that was your attempt to make an AZ. I could tell because I knew what you wanted to do, but yeah, there we go. Right, and if A is less than 1, if it's but still positive, we would have something. Here, let's do a different one. Here, let's do A less than 1 but be greater than 0, right? Then if I do that in orange, it would be something like that, right? And if it was negative, we'll do this in a different color. Woo-hoo. Let's imagine A is negative. So this would be A less than 0, right? Right. So it's just going to exchange the modulus, and if it's negative, then you get a reflection through the origin. Cool. I like it. I don't know why that was 4A. That was just 4. Let's do 5. I'm still in red. All right. Graphically, what does the operation Z squared over Z modulus do to Z? What? So we'll do the same thing. So first of all, we're going to write Z squared over modulus of Z. So let's make I'm going to draw it underneath here because I'm going to potentially write some more next to that. So again, let's put Z right there. Anyone want to take a shot at this? Yeah, Harry.
So since we know that the magnitude of z equals z squared that normalizes z to a length of 1.
So okay, so z over modulus z, and it's a little, we use the term modulus instead of magnitude for complex numbers. Z over modulus z would normalize, that would be something with a modulus of 1. So we can break this up if you want to then, I guess, into z squared is equal to z times z over, I'm sorry, z squared is z times z. So we could write this as z like that. Wow, forget what I just did that. Does this help us with anything? It could. Or you can take it, someone can take it a different way. So this, so that the fraction there is going to have modulus of 1, but it's got a phase angle still. So I'm going to do something different, actually. I like that, but it might be easier if we do this a little bit different way. This is more lines than I meant. All right. Oh, have I run late? It is 2:30. I am so sorry. All right, let me finish this one. I'm really sorry. I just lost track of everything because, you know, complex numbers. So I'm going to write z is equal to modulus of z, so squared, times e to the I theta, quantity squared, and then divided by modulus of z. Yeah, and Camille, go ahead. You can catch the last minute of this recording too, if you're curious about this. Plus, I'll also just post it, the screenshots. So we can cancel one of these factors of z, modulus. Let's do that. And
How'd you get the e to the I theta?
oh, because remember z itself. So I'll put it off to the side here. Z is equal to modulus z times e to the I theta, right? This is our polar coordinate notation. And so then I squared both of those terms when I squared z squared. Cool. Oh, here, I'm actually going to group the z e to the I theta back together again if we want to. And I could write this as, and so I could have done this, whoops, I don't want to write it like that. I want to, I'm really sorry. I could write this right here, the first two terms, this bit right here, as z, and then times an e to the I theta, right? And so what that's going to do is, if that right there is theta, then what we're going to do is rotate this by another theta. And so it will keep the same modulus. So this is z times e to the I theta, which is the same as z squared over z modulus. And the way Harry had written it was talking about it, if we'd written this as z times z over z modulus, then we would have gotten, actually in some ways, maybe more directly to this answer right there. Right? So doing this right here, we've multiplying by z over z modulus basically added on an extra theta to our phase. We multiplied by an extra e to the I theta phase factor. Cool. We'll stop here because I'm already over. What we're going to do is start using this to describe waves when we get back. I will talk through some, not every single one, but a couple of the last little bits there on this practice when we get back. So I will see you all Friday. Take care. Feel free to email with questions on the way or in between. See everyone. Be well. All right. See y'all.